Okay, I'm back, and now we want to use the concept of the arc second in order to figure out the distance to a star. Now, in Unit 4, we're going to find out that there are other ways of measuring the distances to stars, but we're going to start off with relatively close stars to Earth, and we're going to look at the method that is used to measure the distance to them. And so we're going to call this the parallax method. And so in order to do this, it's audience participation time. So what I want you to do is to hold your finger at arm's length, okay? And then I want you to close one eye and then open it and then close the other eye and then just go back and forth from one eye to another. I bet you look pretty silly doing that, but anyway. Do you notice that your finger appears to be moving back and forth with respect to the background? So if you're holding your finger up and then you look past your finger, you see a wall or something, then in relationship to that wall, you should notice that your finger is moving back and forth. Now, it's not really moving back and forth. It's an optical illusion because you're using one eye and then you're using the other eye. So let's try to do that with a star. So if you go out tonight and you look at a star, try going from one eye to the other eye. It doesn't work, okay? That's because your two eyes are too close together. So if somehow you could pluck out an eyeball and have it over here, and then have your other eyeball over here, and then you'd probably look like some alien from Star Trek. But let's assume that you could do that. That would improve things. But still not enough to be able to see a star moving back and forth. So what we do is we take a picture of the star, let's say in January, and then we take another picture of the star in July. So that's equivalent to taking your eyes and have one eye on one side of the orbit of the Earth, and the other eye is at the other side of the orbit of the Earth, and now your two eyes are far enough apart that when you take your pictures, you'll notice that that star is going to appear to move back and forth, again with respect to the background. In this case, the background would be the background stars. And so that's illustrated in that picture there. So we could do some trigonometry because we've got like a little triangle there, and we could solve it for the distance from the sun to that star, which is essentially the distance from the Earth to that star, because of those stars are so far away that essentially those two distances are the same. So we're going to say that r is going to be the distance to the star, and it's going to be equal to 1 divided by the parallax angle. And the parallax angle is given by this letter here, which is called a theta, and it looks like a circle that has a little thing through it there, but it stands for the angle. It's the parallax angle. And you can see where the parallax angle is in that picture. So astronomers can measure that angle by noticing how far back and forth does that star appear to move, depending on whether it's January or July. So we're not going to get into it as to how they do that. We're just going to say that they can measure that angle, and that's going to be theta, and it's going to be in arc seconds, so that thing that had the double tick mark. And then when we plug it in, the distance r is not going to be in meters. It's going to be in a special unit that's going to be called the parsec, PC. So 1 parsec is equal to 3.26 light years, and it's also equal to 3.09 times 10 to the 16th meters. And that is approximately the distance to Alpha Centauri. Now, it's not quite, because we know that the distance to Alpha Centauri is about 4 light years. But just for the sake of argument, that gives you a rough idea for how big a parsec is. So let's try it. So let's take this formula, and this formula is really, really easy to use. So how far away is a star if it has a parallax angle of 10 arc seconds? So the angle is going to be 10 arc seconds, and we want to know what's the r. How far away is it? So we're going to take our formula, r, 1 over the angle. So it's going to be 1 divided by 10, and you probably don't even need a calculator for this. So 1 divided by 10 is 0.1, and then the unit is the parsec, PC. Now we could go backwards as well. So in example number 2, what is the angle, what's the parallax angle, if a star is 20 parsecs away? And so let's say, here's our working formula, and let's go ahead and multiply both sides by theta. So then what you'd have would be theta r is equal to 1. Well, that's still no good. So what we need for it to say is theta. So now we're going to divide both sides by r. So that means that theta is equal to 1 over r. Now, you don't really have to memorize that. Just know that they're opposites. So the theta is in the bottom part when you want to get the r, and the r is in the bottom part when you want to get the theta. So they're inverses of each other. So in this case, we're going to plug the distance of 20. So we're going to do 1 divided by 20 on your calculator, and that turns out to be 0.05. But don't leave it just like the number. You need to put a unit on the end of it. So it's an arc second. So you could write the word arc second, or you could put the double tick mark. So now we know how to measure the distance to close stars. So stars that are roughly up to 100 light years away from Earth. Now, if we want to go further than that, we're going to have to use a different means, and we'll discuss that in unit number 4. Okay, so our next thing that we want to measure is going to be the brightness of that star, and we're going to do that in our next segment.